Hello, and welcome to Our Earth, its climate, history, and processes. I'm David Schultz. In this lecture, I want to discuss the transition between the Hadean and the Archean eons. Recall that the Hadean is the time right after the formation of the Earth when the Earth's surface was mostly molten. It was during this transition that the crust started to cool, the oceans formed, and the first continents were created. With the leftover heat from the formation of the Earth and more radioactive elements present inside the Earth, the mantle was warmer and more actively convecting. By one estimate, there was 3 times the amount of heat flow from the interior than at present. Within the context of this more vigorous convection, the pieces of the Earth's crust that formed during this time were smaller, and there were many more of them than there were at present. Numerous volcanic islands were likely also present. The upper mantle was partially molten, with lots of magma being generated. When this magma erupted onto the surface, thick oceanic crust was formed that wouldn't subduct because of its buoyancy. Over time, this buoyancy and the thickening of the earliest continents would give the cratons their stability. For example, the craton of North America is 250 kilometers deep. There are 2 types of Archean crust that we see at the present time. One is the so-called granite greenstone terranes. Greenstone is a low-grade metamorphic rock derived from mafic volcanics. Although their origins are controversial, they are probably oceanic crusts that formed at spreading centers and were engulfed by granitic intrusions. These weren't mid-ocean ridges as we think of them today. The other type of Archean crust is high-grade metamorphic terrain. These are metamorphic rocks that are derived from compression, burial, and subsequent erosion of granitic crust. These are similar to the deeply eroded mountain chains that we see at present, but they aren't linear like mountain ranges that are formed from subduction zones or continent-continent collisions. They are more circular or S-shaped, again consistent with the fact that plate tectonics as we know it was not operating at this time, and that the plates were smaller and more circular. This era is sometimes also called the flake tectonic era, because the plates that existed at this time resemble smaller flakes rather than more highly structured plates. By 2 billion years ago, the first evidence of island arcs and subduction seems to have been present. Deformed sediments in the trenches of these subduction zones and andesitic lavas began to appear. Whatever continents were formed by then now became fixed. New crust that was created from island arc volcanoes would result in an increase in the amount of continental area. This process by which new terrains were created and emplaced upon existing cratons is called accretion. So, what about other planets? What happened there? Let's take Venus, for example. Here we see a comparatively smoother surface than we see on Earth. There are fewer craters than that on Mars or on the Moon. The dating of these craters implies that the crust on Venus is not much older than 750 million years ago. The lack of old craters implies a complete resurfacing of Venus. One might imagine a situation where insufficient heat is released from the interior of Venus such that eventually you get this catastrophic event with eruptions and remelting of the surface crust. One reason for this is the lack of water on Venus. Venus lost almost all of its water, and without water, as we'll see, there's no lubricant for plate tectonics. So, that may help explain why the evolution of the lithosphere on Venus is so much different than that on Earth. If we look at Mars, we see no active plate tectonics. There are some valleys on Mars that may represent old plate boundaries, but there is nothing active. Being smaller and further away from the Sun, Mars likely has cooled much more quickly to the point where plate tectonics have stopped now. A similar fate may be in store for the Earth eventually, but we have no evidence that plate tectonics is currently slowing down enough to be observed. So, what did we learn from this lecture? On the early Earth, the mantle would have been much warmer and more convective. This early crust that was forming in cool regions on the surface was too buoyant to subduct. This new crust constituted the cratons, the kernel of today's continents. As the Earth cooled, the convection in the mantle slowed down, the size of the plates grew, they traveled more, they had more time to cool, and subduction started. This ushered in the era of plate tectonics.